This week's episodes were brought to you by the generous support of Yukofin. Hey folks, Quilly18 here, and welcome to another episode of our Unity project, codenamed Project MightySpud, where we're trying to make a terrain engine over here, and we are very near the end. In fact, I am going to be starting on the very last major feature today. It's been a little while since the last episode. I was out of the country for a while, and then I did a mini tutorial, but oh, that was the other big thing. Aha. Okay. No, we're not quite started on the last major thing yet. The last major one is going to be the movement from the surface to orbit and back. And I think that's actually going to be okay, actually. I think we've done a lot of good work that will make it relatively useful. What I forgot was that I have to smooth out the terrain underneath this thing. Got to smooth it out right over here. So that's what we're going to work on today. But first, one of the advantages to having waited for a bit and then getting to read a lot of comments and having a couple people tweet at me is they pointed out that one of the reasons the seams are a little bit more pronounced than they should be is because I have a slight error in my math. And I know what you're going to say. That's never happened, Quill. You never, ever make a math mistake. But this time, it happened. It's true. Just a tiny one. It's not the only thing that's stopping them from being seamless. It's still because you cannot have a perfect transition from a sphere to a flat surface. So there's always a little bit of distortion that we're going to sort of have to fudge in the edges at some point, but we may not worry about it quite yet. But one of the things is right over here, right? I keep talking about normalizing these, say, x pos and y pos as a value from 0 to 1, but that's not actually what's going on here. Because if you look at the math, what's happening is x loops from, say, our map width is what? Whatever it is. Let's say train data.height map width is 100. It's not, but let's just say it's 100. So x will iterate from 0 through 99, right? Because it's going to stop after x stops being below that. And that's correct. That's the correct number of iterations. However, it means that over here for x pos, we are not going from 0 to 1. We are going from 0 to, in this case, 0.99. But we actually do want it to go from 0 to 1. So what we have to do is we have to make sure that this gets reduced by 1. So now we are dividing x by 99, which when x is 0, we get 0. When x is 99, the biggest value x will ever get, at 99 divided by 99 will be equal to 1. So we have to do that here. That's, I think, the major one for the seam, but there's a couple other places where we make this sort of assumption. So we're just going to scroll through. Luckily, I think I mostly usually have this comment over here, but we're going to take a look to see if there's anything else we can catch. This is fine. That's not the kind of division we're talking about here. Right over here is another example right there. So again, it's going to be -1, -1, but because of order of operations, it becomes important for us to wrap this in a parentheses and a parenthesis, and a parentheses, because otherwise it'll do the division first and then the subtraction. So there we go. We've got that, again, for the 0 to 1 kind of value. This is fine. That's okay. Any others? I feel like there might be another one over here. Maybe not. And then that's something else. Okay. So if we were to go and stop. So I'm going to have the camera view in exactly the same place. Now, I think there's still going to be a seam, but I think it would be less pronounced. We'll see what happens when this reloads. Chunka, 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 chunka. Poor computer. Wow, look at that! That's what I'm talking about. Very, very, very minimal seams. There's always going to be the tiniest bit of distortion, and there's still the tiniest bit of gaps because they don't have exactly the same values because of like the spherical coordinate to flat coordinate system. But bam! I think that is more evidence that we've done a pretty goddamn good job. I think we can all pat ourselves on the back that we have done a very, very good thing. Again, there's going to be the tiniest little bit of distortion. At this point, though, it's so small. And that was my entire goal. My whole thing was always like, we're doing things in such a way that the distortions that exist are going to be basically non-existent. And all we're going to want to do at some point is do a run where we go through the seams, wherever the hell they are. I can't even see them anymore. Oh, this is gorgeous. Like over here, go through the seams and just like make both numbers equal the same. We'll just like hard code it. We don't have to go far. I didn't have to worry about smoothing more than one chunk. Just literally right at the seam between the two terrain textures over here, which you can just see. I don't even know if it'll show up on YouTube. I can just see this little dotted line line here because the vertices aren't 100% the same. It's mostly just a math rounding error at this point. But what you can do is go through and make them 100% exactly the same, just by force. Just run a script that goes along here and makes one side equal to the other, or both sides equal to the average. So we'll try to. Hopefully, we'll have time and inspiration to incorporate that. But what I actually want to do this episode, and probably this will take still more than one actually, is the terrain underneath the object over here. Whoop. We need to level this off. That's what our goal is over here. We want to level this off so that it is flat underneath this. So we have to figure out the process for doing something of that nature. And there's going to be a few little steps here. What we're going to have to do is figure out basically every point of our height map that is underneath this. We need to set its height to be exactly the height of the base here. And actually, by the base, I mean we're actually just going to use this y parameter here, right? Sorry, this one here in our cool base. So whatever this y parameter is, because presumably within this, we have correctly set things up that, you know, the 0 marker of this internally is the floor. And that's true. Our concrete is elevated by 0.5 units because it's 1 unit tall. So, and it's set in the middle. So the bottom of this concrete is the 0 point of this cool base, or whatever this y is set to. So if everything below this has the height set as the y, then it's going to be nice and smooth. But that's not the simplest thing to do, interestingly enough. So what we have to do is, in our dynamic terrain chunk, we have, presumably in here somewhere, the code that places the building. Build structures, there we go. Build structures over here. So this is plopping down a structure here. So what we want to do is, after a structure gets plopped, what we want is some sort of function here. Maybe I'll move it down to the bottom. Void smooth terrain under structure. Okay, pretty clear what it does. And I guess we'll take the game object of the structure game object, like that, because we grab it over here, the structure. We don't do anything with it, but now we can do something with that. So we're going to call smooth terrain under structure for the structure. Okay. So what we have to do are a few things. First, we need to figure out the bounds for this structure. Now, it's kind of interesting. The problem is, well, it's not a problem, but let's discuss something that might not look right at first, and we'll see if we can tune it. Part of the problem is when you have a structure that's diagonal like this, right? If we just do the bounds in normal coordinates, what's going to happen? See the square that I'm highlighting? Okay, not anymore because I've just zoomed in. Hold on. I'm trying to give a better view and then forgetting it'll change it. So this square like this. This is basically the bounds. So we're going to be raising the terrain, everything underneath this highlighted square, which means including this corner over here. Now, technically, that doesn't necessarily have to happen. Depending on how, you know, the resolution of this mesh, it's entirely possible that if there's a point here, we could ignore it. Instead, we just need to raise the terrain under this point, and this point here, assuming that's the resolution of the terrain. And I guess we can actually tell it here, right? So, assuming each one of these little crossing points is a point that we can mess with, okay? Then really, we only have to raise these up here, 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 and so on. Whereas if we have this as our bounds, we're going to end up raising all these guys, and that won't quite be right. What we're going to do is we're going to use that as our first pass anyway, and then we'll figure out if there's a better way to make this fit afterwards. Well, I didn't want to turn it off. I want to keep it on here for visualization. I guess one of the things... See, what I was going to do is just calculate the bounds. Basically, find out the smallest x and the biggest x, the biggest z and the smallest z, and then use that as our defined corner. And that's a very, very fast way to do it. It's also very simple to implement. But the other thing you could do, and especially if you ended up with something that's an irregular shape, is we could do like a raycast. What I could do for every point of the mesh, I could start with the bounds. I could figure out the bounds first, okay? Then for every point in our terrain mesh within those bounds, I can look at this point and ignore the height. Like set the height to 0, and then do a raycast upwards to see if it hits this object. If it doesn't, then I ignore it. If it does, then I change the height. The only downside with that is it's possible for, let's say there's a point right here, so it hits the raycast and goes even, and then the next point is over here, so it shoots up and doesn't have anything underneath it, so it doesn't raise itself up. And the problem is, in that case, we'd still end up with something kind of like this, right? Where this part here got raised up to meet our surface, but this part right outside didn't, so we still have a bit of an overhang, which may or may not be okay depending on things. Whereas the nice thing about the bounding box, what you can do is you can, like, it's easy to just increment it to the next tick up so that you can make sure to get all the border territory. So we're going to start with that, and we'll see if we can come up with a gooder solution later on. Gooder is fine, shut up. One of the things, actually, it's going to come up is we are going to have to find out, sorry I keep closing this and then realize I want to keep it open for an example, is we have to figure out how to calculate our bounding box for our object over here. Now, as long as we have colliders in all of this, and currently we do, right? Our concrete, for example, has a box collider. So let's assume the only thing we care about is anything that has a collider. Now, it could be a little weird if something overhanged and we didn't actually need the surface to go up there or whatever, but, you know, then maybe we just model things differently or we figure out something else. But if we've got a bunch of colliders in here, we can iterate through every single collider that's part of Coolbase and add it to a bounds. And that's not too hard to do. So, and that time I meant to close it. So let's say, so we can have a bounds object, right? So this will be the structure bounds, which we initialize to a new bound structure that is empty. Yes. And then for our game object, we do something like, we can get a list of all the colliders in this structure game object dot get components in children of type collider, and this will take in everything that's descended from colliders, so box colliders, sphere colliders, etc. It'll get all the colliders that are a component of this structure and the children. So it's going to list all of them, and then we can do something like for each collider call in calls. Collider has bounds. That's interesting. Box colliders have bounds. And I had assumed that the superset... Oh, it's still just this? Oh, hold on. That's why. There. Oh! I'm an idiot. I'm an idiot. I was looking at the array, not the object. Okay, hold on. Let me back this up again. Once again, just get collider. I'll explain what I was doing and why I was being stupid. So, collider.bounds. There we go. I was doing calls. I was looking at the array. I was looking at the array and trying to figure out why I couldn't get bounds. Okay, the collider bounds. So, bounds is a little structure that describes the size of an object, basically. How much it goes in the x-axis, y-axis, and z-axis. It describes the minimum and maximum. It describes the total extents, and so on and so forth. And what's great about them is you can actually combine them. So what you can do is your structure bounds over here, you can go and say, do you want encapsulate or expand? I was going to say encapsulate. Expand the bounds by increasing its size by amount. Oh, that would be amount. Yeah, so encapsulate like this. So what it will do is it will grow this volume. Basically, bounds describes a volume, and it will grow it to include the next one in here. Now, I think if we do this this new bounds over here is initialized by default at the 0, 0, 0 point on the map and with a size of 0, 0, 0. But it means as soon as you add one more bounds into all of this, this object here, structure bounds, will encompass the area from the 0, 0, 0 point to wherever the hell this actual collider is positioned. So you get a ridiculously over large structure bounds. So what we actually want to do is we're okay with starting this as a null. Start it empty. And then say something like, if structure bounds is equal to null, then instead of instantiating it with a blank, we can say, can I say new bounds and then pass it one to clone from? That's a little odd that you can't. The problem is, and I should check the documentation right now, Unity bounds. I'm pretty sure if you were to just instantiate it like this, it would not do what we want. I'm just really surprised that it can't be instantiated for another one. I mean, I guess we can still do it. We could do something like new bounds, and then use this version where it needs a center. So call.bounds.center, and then call.bounds.size. That's going to be okay. So if it was null, we just set it to this one. Else, that's when I do the encapsulate. It may not be required. It's possible that a previous structure was working, but this should also be okay. I guess what we could have also done, and this would have been acceptable-ish, is we could have instantiated this one with the position of the structure game object with the size of nothing and then had it grow from there. But it's possible, even though it would be pretty stupid to do it this way, it's possible that our structure, that the actual objects in it are like offset from the actual game object itself for some bizarre reason, and it might lead to weird things. So anyway, if we've got this, at this point, structure bounds describes the entire volume occupied by this structure, or at least the colliders anyway, right? Anything that didn't have a collider won't be counted as part of this, but we'll just assume that, no, I mean, that's okay. We'll just use that. I mean, you could figure other things out, but this seems like a perfectly fine assumption. Because you might have all sorts of visual widgets that stick outside of your structure that don't have colliders, and you don't want to use it as the base. All right, so now that we've got that, what we need to do then is figure out, now we need to figure out which points of our height map array are under these bounds. And actually, before this, to do, grow the structure size to make sure it overlaps the next height map array index. Mostly going to be a problem if we have a really low res height map array, but technically always an issue, right? And again, it's that thing where depending on where we check, it's possible that a little bit of our structure will sort of overlap a point and it will just overhang, right? That thing where I know I don't have it running anymore. I hope people are following, but like where we had the concrete structure here, and we had that sort of a little bit of that slope, and just at the edge of the concrete structure, because it didn't quite reach, like if this is a point on our height map array, and the concrete structure is like this, so this height map array point will be the correct height. This one here won't get updated, so you'll have a slope that comes down from here to wherever the heck it is, and then you get this weird little overhanging thing. But we'll look at fixing that next. So, so which points of our height map array are under these bounds? Actually, we'll probably fix that here by doing some sort of division. Oh, I like that, actually. Hold on. Okay, we'll figure that out. So we need to be aware of a few things. We know that like the bottom left corner of our terrain is our own terrain object, right? So if we did something like this, terrain bottom left corner, just so that we can keep things straight in our heads, this is actually this game object's, well, this transform dot position. Okay, that's the bottom left corner of this terrain chunk that we're on. And then depending on the resolution, we need to know. Okay, so there's that. And then I guess the question then becomes, we can have, say, a vector 3, just for our sanity, structure, bottom left corner. So that's equal to the structure bounds dot min. This is going to describe the smallest x and the smallest, well, y, but z, right? Because we're dealing with x and z in Unity world space to define this so-called bottom left corner. Because obviously the y in this case would be a height thing. Okay. So presumably, yeah, presumably the minimum, like minimum x is fine, minimum z should also be fine. So really what we have now is the structure position offset, which is the structure bottom left corner minus the terrain bottom left corner. So what this is the position of the structure relative to our terrain. And then what we can do is, I mean, the structure width is easy. Like if we want to note this, right? Structure, well, width and height. It's just part of the bounds. We'll get to it in a second. So what we need to do is figure out the terrain height map array x and y that is described by this. So let's say we make a vector 2. Call this terrain array min. Okay, the minimum position in this. This is going to be based on our structure's position relative to terrain, divided by the, like, the terrain resolution kind of thing. What do I mean by this? Right? Our terrain is 1,024 world units wide. We set that above. But how many array units wide is it? We have a number for that. We are setting it where? I think it's one of those that's getting hard set over here. Yes, it is. Right here, I think it's this terrain data.heightmap resolution. So I think it's this. So, for example, in this situation, so should be, I guess 129? Because it was, I think, was it not 128 plus 1 for this one? I mean, whichever, because we've got a few more. We've got that, we've also got this. But that's different, because it's the mesh. Detail resolution is fine. The size, yeah, so this should be the number. So our internal array should be 129 by 129. So in this case, you have the example of, imagine that our structure is at relative position, say 500. That means it's at array index, I guess about half of this, rounded about like, what, like 60 or whatever, you know, some number. Half of this, 64. Something like that. And we actually do want to round down. The nice thing about some of this, actually, I should, because it's all going to have to be turned into indexes. I guess it'll be at index 64.5, round down to 64. So when we force things into being an integer, this is going to get rounded down. So vector 2 is going to... yeah, I guess a vector 3, because we're going to use the x and the z portion of it. Okay, so that's the min. And then I guess we want the train array max as well, which is going to be... the top right corner, which is the structure bounds max. I mean, I could have used these directly, but... you know what? I will use the structure position offset plus the structure bounds dot size. There we go. So this is the relative position in the bottom left corner of our structure, plus the size is the maximum thing, and then we're dividing it by here. So these are effectively describing array coordinates. So then if we did something like 4 int x starts at the terrain array min dot x integer. I mean, I didn't need the extra pair of parentheses here, but screw it, it's fine. So this will round it down, which is good. And then we want to make it stop at the terrain array max. But what's important here is that we don't let it round down. In fact, we want to bring it up by 1. Or do we want to add it up by half a unit or something weird like that? It's possible that it's right on the spot. It would be weird and rare. I could have it be like 0.99. You know what? 1's going to be fine. Very rarely will it overlap by, like, literally too much. Only in the time when it's exactly equal. There. It's fine. Okay. So we've got that. We'll do a similar loop in the, well, sort of y direction, but note that these are going to be z coordinates. I know, it's really confusing, but world space y is array... world space z is array y. World space z is array y. So I guess we could get the entire height array, but that's... we don't need to actually grab it all. I mean, if we did, we would do this. And then we'd be setting our heights at x comma y. Except I think they're actually inverted, so we'll have to check that. Let's set this to the max as a test. So this is grabbing all the heights, which we don't need to. We could optimize this to not quite do as much. But let's say we do that. And then come here and say, I guess, set heights. And then pass it 0, 0 heights. We can grab a smaller area soon. So first, let's check to see if there's any syntax errors. Cannot convert null to... oh. Okay. Ooh, so you can't... wait. So you can't ever check it to null. Okay. Oh, let's tell you what. Let's go ahead and run just this and see if it ends up with an area that's way too big. In fact, if it's way too big, it'll probably crash because it's going to do probably an out of bounds thing somewhere. Because this is going to start off like negative. But now you're saying it's... okay, so I have to say new. Okay. I feel like there's something I'm going to be unhappy about here. Let this run, let this run, let this run. Yes, out of index, that's expected. because this is doing the thing where it's starting from the 0 point. So, okay, what if then I can start this? I will sort of cheat. Well, first of all, if calls dot length is equal to 0, we should put a little check in here. Debug.log error? I don't know if it's an error or just a message, but let's say an error. We'll say structure has no colliders, question mark. We'll return that. But assuming calls is not 0, then there's at least going to be 1. So we can grab the first one. So calls 0. We'll do that. I mean, we don't even need to set the size, but it's okay. Now, technically, that means the first one in this list is going to happen twice unless we change this to a for loop, but that's okay. Hardly the end of the world. Encapsulating the same bounds twice is not going to make a difference. Okay. So again, no compilation errors. We're going to hit play. Let's see what happens. Okay, well, first of all, no actual errors, which I think is as surprising to me as anyone. Secondly, what? Hello, that's good. Okay, I mean, it's wrong, but it is wrong in a... That's actually not what I expected at all. Again, I think you're going to have to invert the X and the Y, but that, to me, would have meant that our little spire would be over here. Also, I don't think it should be a single point. Although, I don't know if it is a single point. I don't think so. To me, it looks like it's got a square top. So I think it is doing more than one. But, what a surprise. There's a little bit of a little math whoopsie-doo somewhere in here. So we're going to have to put a cut in here because it's gone quite long. But we are definitely on the right track. We're going to figure that out. Again, I'm sort of expecting what's going to happen is we're going to get an area of this terrain roughly this big over here that's going to be set to a height of 1. That's the immediate goal. Let's find out what happens next time. Thanks for watching. See you then. Thank you to all our April Patreon supporters and these Mic Check supporters. We've got Harry Hendel. We've got Yukofin, Snoopy TRB, Tiburon, Pavel Zdanov, Drazion, Gavin Power, Michael McClintock, Aaron Toibson, Greg Mortel, The Not So Evil Engineer, Julien Auger-Lafont, Maris Fieldvold, Speedy Savant, Steven Stagger, Valiant Cake Fiend, Jason Yanity, Steven Bonnerman, Kale the Quick, and Neil Blakey Milner, and everyone who's watched, shared, favorited, and subscribed to these videos. Thank you so much.